to go over a couple of things that come up in circuits 2 that I don't think really get adequate coverage in circuits 1, and you really can't find this in the textbook the way I like to do it. So in fact, they kind of dropped it from your current textbook overall. So what I want to look at is I want to look at an RLC circuit. This is a second order circuit. So C, R, and L. And we're assuming here that we have some initial charge on this capacitor, and then that this switch is closed at t equals 0, and what we'd like to know is what is I of t in the circuit. So the first thing I'll do is I'll transform this to the Laplace domain. So the capacitor will go to 1 over SC. The initial condition on the voltage will keep the same polarity and go to V naught over S. I have R, and I have SL, and then, and then my current becomes I of S. So everything's been transformed, and this is a single loop, so let's write the single loop equation. I have minus V naught over S plus I 1 over SC plus I times R plus I times SL 0. And doing a little bit of simplification, I have I 1 over SC plus R plus SL is V naught over S. So I times 1 plus SCR plus S squared LC over SC is V naught over S. So I is V naught over S times, inverting this fraction, SC over S squared LC plus SCR plus 1. Okay, note now that the S is canceled, and what I'm going to do is out of the denominator, I'm going to factor out an LC, because remember, in transfer functions, you always want the highest order of the polynomial to have a coefficient of 1. So factoring out an LC, S squared plus S R over L plus 1 over LC. And simplifying one last thing, that gives me V naught over L S squared plus S R over L plus 1 over LC. So in the numerator, I just have a constant. So when I take the inverse transform, that's just going to come out to the front. So let me add a slide. And let's go back. So V naught over L over S squared plus SR over L plus 1 over LC. Now remember, when you have quadratic in the denominator, remember first of all, it is the denominator that determines the response in the time domain. So as long as the denominator is of higher order than the numerator, your response on the time domain is what's good. Your denominator in the S domain is what's going to determine the mathematical form of the response in the time domain. So these quadratics, as you know, quadratic can go one of 3 ways. It can be a double root, perfect square. it can be two real roots that are distinct, or it can be complex conjugate pair. If it's a double root, then you end up with a result in the time domain that looks like some a e to the minus alpha t plus b e to the minus beta t, where a and b are constants. If it's two real distinct roots, scratch that. So let me erase that. If it's a double root, let's start over. If it's a double root, you get an a times t e to the minus alpha t plus a b e to the minus alpha t. So a single time constant, because it is a double root, and then you have this t here because it is a double root. Okay, the other option is two real distinct roots, which I mistakenly wrote before. That would give you e to the minus alpha t plus b e to the minus beta t. So two different decay rates, i.e. time constants, 1 over time constants, and two different constants determined by the initial condition. And there's also the complex conjugate pair, which we know gives us something of the form a e to the minus alpha t cosine omega t plus, where this is some constant omega, plus b e to the minus alpha t sine omega naught t. So those are the three possibilities. So let's look at this denominator. Go back to black. So I have s squared plus s times plus L over R times s plus 1 over SC. So if I use the quadratic formula, S will be minus R over L plus square root of R over L squared plus 1 over, or minus four over LC all over 2. So now I'm going to take the 2 up to the numerator, and under the square root sign where it becomes 4, and then inside these brackets it'll become 2 again. So algebraically it's minus R over 2L, and this is a plus or minus the square root of R over 2L squared minus 1 over LC. Taking this 2 in, cancel that 4. Okay, let's add another page, and let's go back. So my roots, which is actually 2 roots, minus R over 2L plus or minus the square root of R over 2L squared minus 1 over LC. And what I want to focus on is this term right here, because it's what's really going to determine the kind of roots that we have. So if R over 2L squared minus 1 over LC is greater than 0, then what we will get is 2 distinct real roots. And that kind of a circuit has basically 2 time constants, and it is referred to as an overdamped circuit. And what it looks like is I starts at 0 because it has to be 0 because the current through an inductor can't change instantaneously. comes up and then it slowly decays in time. Okay, so that's option 1, overdamped. Option 2 is that R over 2L quantity squared minus 1 over LC is equal to 0. In that case, we have a double root and a single time constant. And this is referred to as critically damped. And that response has a little bit higher peak, a little longer rise time, but the energy is concentrated. It's more like a pulse and less like an RC decay. Okay, finally, the third possibility is that R over 2L squared minus 1 over LC is less than 0, meaning there is an imaginary quantity or there's a negative quantity under the square root sign. So that'll give us complex conjugate pair. So that's a complex conjugate pair roots. And that's referred to as an underdamped circuit. And it is a decaying oscillation. So there we would have something that looks like this. You could also, just depending on the relative relationship between the frequency and the decay rate, you could have something that looks like that. But you have this oscillation, and if you could visualize like an envelope around that, that represents the decay. So this is the e to the minus alpha t part, and this is the cosine or sine or sine part. So the RLC circuit, the point is the RLC circuit can give 3 possibilities. Now what do the possibilities depend on? They depend on this relationship. So if we add one more, so R over 2L squared minus 1 over LC. So they depend on this relationship. So is it greater than, less than, or equal to 0? And depending on which one of these is the case, and what's going to determine which one is the case, well, basically the relative relationships between the R's, L's, and C's. So if R over 2L is greater than the square root of 1 over LC, you could do some rearranging. You could square both sides. R squared over 2L squared greater than 1 over LC. You could multiply through by L and C, and you would get R squared LC over 2L squared greater than 1. You could get some L's to cancel. Tell you what, just for fun, let's play with this isolating the resistor. So R squared be greater than 2L squared over LC. R squared greater than 2L over C, or R is greater than the square root of 2L over C. If this is the case, you have overdamping, because that would give you a positive number under that radical, so you'll get 2 separate roots. So what does this tell you? This tells you if you have a circuit and L and C are fixed, that if R exceeds a certain number, namely square root of 2L over C, your circuit overdamps. Now, if we decrease the resistance, so we're looking at this circuit, if R gets smaller, then what happens is you move away from the greater than and you move to the equal to. So all things equal, okay, decreasing R takes you from overdamped to critically damped to underdamped. As R goes to 0, the circuit becomes a pure oscillator. Just a pure LC oscillator. So, so you can do different things with this RLC circuit depending on the output that you want to get. Most of the time, inductance is an unwanted thing. Most of the time, you would like for your inductance to be closer to 0, because usually inductance is what's going to introduce that ringing. On the other hand, it's the inductor that allows you, if you want to, under the critically damped case, if you want to, you can get this pulse. And I'm drawing this as it's skewed. It's actually not. That's just a bad drawing. It's not symmetric, but it isn't as skewed as I'm showing it. So this critically damped, it's used in things like pulse power, etc. If you have energy stored in an inductor and you want to switch it off to a resistive load, basically if you design it to be critically damped, you're kind of optimizing the way in which you transfer the energy as far as a trade-off between speed of getting the energy out of the capacitor and avoiding the oscillations that you will get if the system is underdamped. Part of the problem with an underdamped circuit is this ringing and the fact that it's going negative. In some applications, you don't want to reverse capacitor voltages. If you have extremely high energy density storage capacitances, you don't always want to reverse the direction of the voltage polarity, especially not rapidly and not to a huge extent. Some of them can take a small reversal, maybe a 10 or 20%. But if you try to reverse the voltage completely, you blow the capacitor up. So the critically damped circuit is the one that is most often used in capacitive energy storage and transfer, simple kinds of circuits. All right, so you can actually determine, given an RLC circuit, from the values of R, L, and C, whether it is underdamped, overdamped, or critically damped. And you can do that with these criteria. So this is going to be an important thing in this